I've been working on a tiny chess bot. Recently, Sebastian Lague posted a chess programming challenge, and this is my response to that. So, what does tiny mean in the context of this challenge? It means I have to write my bot within the limit of 1024 tokens. But what is a token? Well, a token may be a variable name, an equal sign, a function call, a pair of brackets, and so on. You get the idea. More on this later. So, how does a chessbot work? There's two steps, searching and evaluation. Let's start with the search. In the search, I implement a bunch of features like the transposition table and move ordering. I'm not going to go in depth over each of these. I didn't do anything particularly special. If you want to learn more, I recommend you watch Sebastian's two videos on his chess AI. They're really good, I promise. Instead, I'm going to focus on what I did differently, which brings me to evaluation. As a basic start, we can assign a value to each piece. Then we can count how many of each piece there are. If it's a white piece, we're gonna add to the score, and if it's a black piece, we're gonna subtract from the score. For example, on a starting board, the score is 0, since both sides have the same number of pieces. If I take a black knight away, for example, we're gonna have a positive 320 score. If I take a pawn, that's 100 points for white. If I take a pawn from white, that's negative 100 points, and so on. This doesn't make the bot very smart. It can't see far enough into the future. If it can't figure out how to win material in a few moves, then it will just aimlessly move pieces back and forth. Not very exciting. It will take a queen if I offer it to it though, so there's that. A way to make the evaluation better is using a score table. For example, this knight table here. A knight in the center is worth more points than a knight in the corner. This will encourage the bot to place pieces in sensible positions. This is what Sebastian does in his videos. However, this is a big memory structure and it will eat up a lot of bot capacity. So we're not going for that. What I did instead was give points to every piece based on how many squares it has available to move to. I think this captures a lot of the same intuition as the score tables. A knight in the corner is still bad, since it will only have 2 available squares, compared to a knight in the middle, which has 8 squares it can move to. Moving pawns in the center is also encouraged, since it gives a lot of opportunities for attack. For example, if I move the d pawn, I get a lot of points because the bishop has more available attacks. Something else to consider. I don't want to encourage the queen to go in the middle of the board in the first few opening moves. This is why I have a separate table for early game and late game. Bishops and knights have higher scores in the early game, since that's the pieces I want to develop. I arrived at these values after a bit of tweaking and testing, so maybe they're not quite perfect. With the bonus points, this is where the bot really came to life. Instead of aimlessly making moves, shuffling a rook back and forth, the bot actually makes good moves, even in the opening. Another small thing I did with the evaluation is add a tiny amount of randomness. Just a random value between -1 and 1. Even with the bonus points added, a lot of moves get the exact same evaluation. This way, the bot can pick any of those moves. One final thing I did to the eval is extra points for pawns, which means bonus points for passed pawns and penalties for doubled pawns and for isolated pawns. To check whether a pawn is passed, I compute this bit board for each pawn, which has the three files in front of the pawn. If there's any pawn of the opponent in this bit board, then it's not a passed pawn. If there isn't any pawn, then it is passed, and this pawn will get extra points. We give extra points based on distance to promotion. This way we encourage the bot to actually advance and promote passed pawns. Then there's doubled pawns. For every pawn that shares a file with another pawn, we apply a penalty. For example, this board is fine, there's no double pawns. This board will get the penalty applied once, this will get the penalty applied twice, and so on. Finally, isolated pawns. For each pawn, we check the adjacent files. If there is no friendly pawn, then that pawn is isolated and it gets a penalty. After adding all that passed pawn business, the bot exceeded the brain capacity. We are now almost at 1200. At this point, my goal is to be under the bot capacity without removing any of the features. So, how do I go about shrinking the capacity? As an example, take this for loop. We can remove this if statement here and simply put it in the condition of the for loop. We're never going to reach this condition for the depth anyway, so we may as well remove that. I can also remove the curly brackets around the for loop. And we don't really need to declare this variable here. That can just go directly in the condition. I've done a bunch of small tweaks like this that got me some bot capacity here and there, but the big improvement was with the transposition table. Having it as a separate class, well, that's a lot of brain capacity. Instead, I can just have a single array of table entries. These table eval type in I'm just going to replace that with raw numbers. Every time I use the enum, I lose 2 bot capacity. Not to mention the capacity to actually declare the enum itself. This is slightly less readable, but I only care about brain capacity right now. This function call to get a value from the transposition table, well, I only use it once, so this function can go away. I can just inline it in the place where I need it. This whole transposition table business saved me about 90 brain bot capacity. Here's something else I did that's perhaps a bit unhinged. I used to store a reference to the board and the best move as class members. How about I don't do that? I'm just going to keep these variables in the scope of the function. Every function that needs access to it, it can just be nested inside of the think function. I think this is quite hilarious, since the only function my bot has is the think function. Everything else is just nested inside of it. After all these modifications, I got my bot down within capacity at 10,019, and I didn't have to compromise a single feature. So, where did my bot end up ranking in the tournament? 76th. I am happy with that result. Had fun making the bot, and I learned a lot from making it. I also learned a lot from watching everyone's different bots in the tournament. It's clear to me that the bots ahead of me did a much better job and implemented way more complex features than I did. Turns out the top bots did squeeze a score table in there. I was probably wrong to dismiss that. Also, I'd like to point out these 2 lines of code in the bot small.cs. This handles passed pawns and doubled pawns. And this is what my code looks like for evaluating pawns. Yeah, significantly more code, I know. That's it from me. I'd like to thank Sebastian for hosting this challenge, and thank you for listening to me ramble about my code for 10 minutes. Cheers!